Alright, so now let's talk about rice tables or ice tables, whichever name you prefer. But I'm just going to go through one of these practice problems because I know there are a lot of good resources out there on maybe some good YouTube videos that dive deep into these ice tables. But I'm just going to go through sort of the basics of how to really approach these questions. So, number one thing you want to look at is what they're giving you. So we have 5 moles of H2, we have 7 moles of Cl2, then we have 3 moles of HCl. Right away, I'm just going to write the balance equation. So it's H2 plus Cl2, and then that goes to 2HCl. So those are balanced, and it is placed in a 1 liter container, allowed to reach equilibrium. And it says find the equilibrium concentrations of the reactants and products if Kc equals 30.5. So automatically we're already given our values over here. So these represent our initial concentrations. So if I do write the rice table over here, so this is going to be our reaction. So this is R stands for reaction, I stands for initial. So initial, we have, when we need to convert this to molarity, the concentration. So this would be 5 moles over 1 liter. So moles over liters gets us molarity, and that's just going to be 5m. And over here, same thing with chlorine. And luckily, this question just says 1 liter, so 7 divided by 1 is just going to be 7, and that's the convenient part. So we're going to have 3 over here. And we have our initials, but we do need to find our reaction constant in order to know which way the reaction is shifting. So, like we talked about how to find our reaction quotient, all we have to do is just use the formula products over reactants, minding the stoichiometric coefficients. So that's H2, Cl2, and that should be, let's see, that would be 3 squared over 5 times 7, and let's see what that gets us. So that'll be 9 over 5 times 7 should be 35. So 9 over 35, and 9 over 35 is also 0.257. So we could just put over here 0.257, and our reaction quotient, which is 0.257, is definitely less than our equilibrium constant, which is 30.5. So the reaction is going to shift to the right. So now that we know that a reaction is going to shift to the right, then our change is going to be minus x over here, and plus 2x. So the reason why it's minus x and plus x is because we're moving to the right. So we obviously know that our reactants are going to decrease. So the change in our reactants is going to be less in equilibrium. So that's why we put a negative x. Now we put a plus 2x. Obviously we put a plus because we're increasing the concentration of products when we shift to the right, because we have to increase the amount of products in order to get back to equilibrium. But we also have the stoichiometric coefficient over here. We have a 2 in front. That's why it has to be plus 2x. And our E, which stands for our equilibrium, is going to be 5 minus x for hydrogen, 7 minus x for chlorine, and it's going to be 3 plus 2x for our HCl. So now that we know that, now we need to find the equilibrium concentrations of the reactants and products. So all we have to do is use this formula again, but it's going to equal 30.5. And we have our values over here. So all we have to do is just plug in and see what we get. So this should be 30.5 equals, and 3 plus 2x, and I'll put a bracket right there, squared over, and that would be 5 minus x. Okay, let me actually redo this. 5 minus x, 7 minus x. Okay, so this is what we end up with, and all we have to do now is just solve it. So if we're going to solve this, it's going to be 30.5, 5 minus x, 7 minus x, and that's going to equal 3 plus 2x squared. And now we just have to do basic algebra. So first we want to FOIL. So first we have, well, I'll just put this 30.5 on the outside over here. So first 5 times 7 is 35. Outside is minus 5x. Inside is negative 7x, and last is going to be our negative x's, so that'll be plus x squared, because negative x times negative x is x squared. And that should equal, if we wanted to FOIL this, then it would be 3 plus 2x, 3 plus 2x. So first is 9 plus, outside is, let's see, 5x, so I'm just going to say 10x, because this is going to be 5, or my bad, that's supposed to be 6. So 3 times 2 is 6, so that'll be 12x, since we have 3 times 2, 6x, and then 2 times 3 is 6x, so 6x plus 6x is 12x. And over here, that's going to be 4x squared. 4x squared. So all we have to do is multiply, distribute 30.5 all over, and so we should get something like this. And now we want to move the variables to one spot. So I'm just gonna subtract this 4x over, subtract all of this stuff over to the left side and make that equal 0, so then I can find x. So we get 26.5x squared, and negative 366 minus 12 is negative 378x, and let's see, 1076.5 minus 9 is going to be plus 1058.5. That is going to equal 0. So now all we really have to do is just solve for x using quadratic formula, but I programmed the quadratic formula on my calculator. You can search up how to program the quadratic formula on TI-84, and there's some great videos showing you how to do that, and it's just much easier instead of trying to solve it on your own. So it's 26.5 as our A, then negative 378 as our B, and 1058.5 as our C. And we get two numbers. We get x equals 10.433, my bad, 437, and x equals 3.827. So when looking at these numbers, we can obviously tell that our number is not 10. Because if we plugged in x equals 10.437 to 5 minus over here, that x over here, then we get a negative concentration. And that's not what we want. We want a positive concentration. So that's why we're using x equals 3.872, because this is just too big of a number and it's going to make our concentrations negative. So since now we know our x, all we have to do is just use this formula again, but we know our x, so all we have to do is for the concentration of HCl, that would equal 3 plus 2, and our x would be 3.827, and that gets us, let's see what that gets us. That gets us 10.654 as our concentration for HCl in equilibrium. Then we can look at our H2, which I think it was 5 minus x, so it was 5x, 5 minus x, so 5 minus 3.827, because we said that our x is 3.827. So that, let's see what that gets us. That gets us 1.173 of our concentration, and for Cl2, that one was 7 minus x, so this is 7 minus 3.827, and that gets us 3.173. 3 as a concentration equilibrium. So we found all of our answers to the question of what our equilibrium concentrations would be, and to check all of that, we can go back to our formula, which was HCl squared over H2, and bracket that HCl2. And if we plug in our numbers, so this is 10.654 squared over 1.173, and then 3.173. Let's see what that gets us. So it's 10.654 squared over 1.173 and 3.173. That gets us 30.497, or basically 30.5 when we round up. And that is exactly how you use ice tables towards finding those equilibrium concentrations. So to break this all down, and it does seem like a lot of math, but number one thing you need to do is find your initial concentrations. If it doesn't tell you what the initial concentration is, then assume it's 0. Second, and if you assume that initial concentration is 0, like for example, if they never gave us the HCl concentration, if HCl concentration was 0, then we automatically know the reaction is going to shift to the right, because it doesn't even start with anything, so the change should be an increase. But since we have an initial, then we have to find our reaction quotient. So actually, let me write these steps, and I'll write them down here as reference. So number 1, find your initial concentration. I'm just going to say just M, just denote as M. So find your initial concentrations. 2, find where it shifts, or where, let's do this, what direction it shifts, it being the reaction. So what direction does the reaction shift? You can either find the reaction quotient, or if you're lucky enough and they don't tell you the initial concentration of one of the products, then that's exactly where it's going. So you find the direction where that it shifts in. And 3, so after you do all of that, then you want to still use your reaction quotient equation, but you want to set up your Rice table. So when you find your initial, you want to see where that change goes. So you put -x or plus 2x, and then you find your equilibrium. So find a direction it sits in, set up Rice table. So set up Rice table. Then let me actually move down here. Then 4. So once you set up the Rice table, then you want to use your equation back again, and basically solve, make it equal to the equilibrium constant. So use QC equation and make it equal to our equilibrium constant. Because like we talked about with equilibrium, in equilibrium, our reaction quotient is equal to our equilibrium constant. So our reaction quotient needs to be equal to our equilibrium constant in order for the reaction to be in equilibrium. And that's why we use our reaction quotient equation in order to make that equal to the equilibrium constant. Once we do that, all we have to do is solve. And if you're lucky enough, maybe you get 1x, but this is a quadratic function, so you're going to get 2x's. Solve, and then 6, pick reasonable x, and you'll know which one's reasonable. More than likely it's going to be the smallest one, but then you have to check. And try checking by plugging in that x and see if this is going to be a positive or negative. And once you do that, all you have to do is plug in x, and that's it. So that's pretty much how Rice tables are used, and it's actually very simple, because you have to understand, in order for a reaction to be in equilibrium, our reaction quotient must equal our equilibrium constant. That's why we're making our reaction quotient equal to the equilibrium constant. That's why we use Rice tables, just to find our concentration in equilibrium.